Sumitra, did you start?
Yes, I have started.
Okay, thank you. The proof of this theorem, even though it's an important theorem, the proof is not that difficult. It's very straightforward. Proof, we show that 1 is equivalent to 2, 2 is equivalent to 3, and then 1 implies 4, and 4 implies 3. That's the way it's shown in the book. To show that 1 is equivalent to 2, again, that's another point when our formula that we saw before is important. So we call the formula that if f is sum j from 1 up to n alpha j k xj, then the norm of f squared is the matrix k xi xj acting on alpha 1 up to alpha n, then inner product with alpha 1 up to alpha. It's very precious formula in CN. And when we look at the statement 1 and statement 2, we see that this identity immediately implies that 1 is equal to 2. Because two means that kx1 up to kxn are independent, and this means that f is not equal to 0 if the vector alpha is not 0. And this is equivalent to say that is not 0 if alpha is not 0, based on the identity. Immediately, we see this is number 1. So 1 is equal to 2. And the reason 2 is equivalent to 3 is based on this formula for any f is in H. What is the inner product of f and alpha I k x I? This is equal to a from 1 up to n. Here you obtain alpha I bar, which is okay, no problem with that. But if you want to have alpha I on the right side, simply here replace alpha I by alpha I bar. That's okay to have bar here, no problem. F inner product with kxi, which is the sum alpha I bar f at point xi. And this is the identity which which shows that 2 is equivalent to 3, because it's based on the meaning of being, instead of saying 2 is equivalent to 3, we can say not 2 equivalent to not 3. In other words, if kx1 up to xk are dependent, then there is a combination here. If dependent, and only if there is alpha 1 alpha n, not all 0, such that sum alpha I kxi is equal to 0. And based on the identity here, this is equivalent to say that for all f in H, well, such that for all f in H, sum alpha I bar f of xi equal to 0. And this is not 2 equivalent to not 3. So in other words, I mean, the notation we use in logic. Hence, 2 is equivalent to 3. The 4 implies 3 is also trivial. 4 implies 3, kind of trivial, because assume without loss of generality, alpha 1 is not equal to 0, because in 3 we assume that not all of them are 0. One of them is not 0. Assume that alpha 1 is not 0, and then put or consider your function f to be g1. Then what do we obtain? We obtain alpha 1 f of x1 plus alpha 2 f x2 xn is equal to g1 x1 alpha 2 g1 at point x2, and g are chosen such that this is equal to 0, except when the 2 indices coincide, which is equal to 1, and this is alpha 1 not equal to 0. So we have a function, a candidate, such that the combination is not equal to 0, and so we have 3. So 4 implies 3. And finally, why 1 implies 4? This is based on previous corollary. 1 means that for any n and for any x1 up to xn, kxi, kxj is strictly positive. In particular, this is invertible. And the corollary says that there is a solution. And there is always an interpolating function. This is the point I used previous corollary. And so this ends the proof. We have number. This is 1 implies 4. There's always more details. Always interpolating function means that doesn't matter what is your lambda 1 up to lambda n. So this means that there is g1 such that is equal to 1, 0, 0. Again, we apply it for g2. There is g2 such that G2 whatever you want to put on the right side is okay, because always. So I put 0, 1, 0 up to 0, and finally there is Gn such that zero. That's the end upstream. So in short, we can say that there is Gi such that Gixj is equal to delta Ij. I mean, this is briefly speaking. So all the time we have a solution, and that's precisely the content of the force statement. Partition of unity, you have for sure not seen this before. In other contexts, we have this in geometry and manifold theory, and even in these studies, G1 up to Gn are called the partition of unity. To Gn, it satisfies the above property, are called, or this set is called a partition of unity. If you know G1 up to Gn, then you immediately have the answer to any interpolation problem, and even the minimal solution that you are looking for. Because if G1 up to Gn are given and you want a function h such that h at point xi to be lambda I, then we can simply take h to be lambda 1 G1 plus lambda 2 G2 plus lambda n Gn. By the defining properties of G, we immediately see that we have this property. And also because each of them, G1, G2, Gn, are linear combination of x1 up to kx1 up to kxn. So H is also in the span of kx1 up to kxn, interpolating in this span. Therefore, H is the unique solution of minimal norm. So the ultimate answer that we were looking from the beginning, uniqueness and of minimal norm, being of minimal norm is important in complex analysis, the solution to the extremal problem. Immediately obtain the answer. Just obtain G1 up to Gn and then do this combination. Then you are done. That's the final answer. It's the good thing about partition of unity. A small section here for best least square approximation. Approximate, as I said here. Sometimes the solution does not exist. I mean, if x1 up to xn in X distinct as usual given, and also lambda 1 up to lambda n in C, this one is also given. Sometimes there is no f in H such that f of xe is equal to lambda a. So interpolation problem has no solution. But still we can ask this question. Consider the quantity, I think it's called J of f, yeah, J of f in the book. J of f is equal to the sum I from 1 up to n f at point xi minus lambda I absolute value squared. So f in h. The ideal is to have f such that each component on the right side is 0, so the sum is 0 and j of f is equal to 0. That's the ideal solution. In other words, interpolation has a solution if and only if j, if and only if there is an f in H such that j of f equal to 0. That's the meaning of interpolation. But if not, give me an f such that j of f is minimal. It's not 0, but it's as close as possible to 0. That's the meaning of least mean square approximation. And so we are looking for an f with minimal error. And the theorem says it's kind of straightforward theorem. Again, the idea is the projection that we saw before. Theorem. Same assumption, x set h RKHS on x. X1 up to xn in x distinct. This is as before. And v, I mean, the vector lambda 1 to lambda n in Cn. And for simplicity, I mean, write it Q here. Q is the matrix K, Xi, Xj. We called this before G for Gramian, but in the book it's written Q. The notation really doesn't matter. Then here is then. There is an existent. A vector in Cn, call it alpha 1 up to alpha n. Cn. Such that V minus Q applied to W. Before, when the solution exists, V was equal to Q times W. It was a solution. But here, V minus QW is not 0, but it's in the null space. In other words, I mean, I'll explain a little bit better. We decompose V as a projection on the null space of Q and the range of Q. If we set, then if we set G to using these alphas, alpha 1 kx1 plus alpha n kxn. Then G minimizes the parameter G that we defined above. Then minimizes J. And also G is a unique function of minimal norm with this property. Again, attention to the uniqueness. I presented the function g, which is a solution, which minimizes j, the quantity j, which was defined here. But I don't say the solution is unique. Generally, there are other g's which minimizes too. However, if we are looking for a function of minimal norm, then it is unique and it's given by the formula which is mentioned here. You see the importance of minimal norm again. True, it's as before. As before, when the solution exists, the solution is not necessarily unique. We can have many interpolating functions. But if we are looking for a function of minimal norm, then it becomes unique. And well, proof not that difficult. Proof. For any f in H, we see that we have a vector fx1 up to fxn. This is a vector for which the interpolation has a solution. It's the function f which is already given. And therefore, this is in the range of Q. By the very definition of interpolation and by the theorem we saw before, why it becomes like that. Then there is, so there is a vector W such that W in Cn, such that QW is our lambda, and our lambda here is f of x1 up to f of x. This is based on the characterization we had in the previous main theorem, that interpolation theorem has a solution if and only if our vector lambda is in the range of Q. And here is trivially the case because f is already given. And so we can write j of f, which is sum j from 1 up to n, f of xj minus lambda j, squared to be sum j from 1 up to n. Well, the sum is not needed. This is QW minus V squared in Cn. V is the vector lambda 1 up to n. And we immediately see that this is minimized. Look, V is fixed, W is changing because our function f is changing. When the function f changes, this W here changes too. And so we have different combination here with V fixed and W changing. And when is this the minimal one? We saw that J of f is minimal if and only if QW is the projection of V on the range of Q. when it's the projection is the minimal one. So in a sense here, it's when you think, I mean, it's kind of trivial that we obtain. Another way to look at this and noting that Q is self-adjoint. Q is equal to Q star. We can write, I mean, Q is equal to Q star. Then the range of Q is n of Q star per in the general case, but here is equal to n of Q. Yeah, because Q is equal to Q star. And so our space Cn can be written as n of Q perp plus orthogonal sum of n of Q and n of Q perp. And instead of n of Q perp, we can write R of Q. So Cn is equal to R of Q plus n of Q. And this is an orthogonal projection, orthogonal summation. So any vector which is given over there, any V which is given, we can project it on R of Q and put this part in the garbage. And this gives us our best least mean square approximation. That's the solution we are looking for. The rest we have already seen that G given like that is the minimizer and so minimal norm. We have already seen. The only observation which is needed is precisely this one. That for any V, the projection is possible and it gives us the best approximation. Well, the last section is probably the most important section of this chapter. The elements of H of K. Why is this important? H of K, its elements are functions on the set X, not all the functions. So it is true that if F is in H of K, then F is a function defined on X, which is values on C. That's by the, main definition. But on the other hand, if F is given, a function given on X, which is values on C, we need some extra assumption. And here is what we want to study. Such that under this extra assumption, we can conclude that F is in H. Very valuable result if we can get it. We will see one of them here. Because in some spaces, like H of B, Dobranch-Rovniak space, Dobranch-Rovniak space, we start with the kernel K. K of Z and W is given by 1 minus BW bar BZ, 1 minus W bar BZ over that. That's a kernel. Well, it's an exercise. Suppose that we can show that K is bigger than or equal to 0. We pass this story, so we have a space which we can denote it by H of K or sometimes by H of B. H of B is more common. Good. Now, what are the elements of H of B? And it's a very difficult question. And still, a clear answer in a sense that we have the answer for Hardy space or for Dirichlet space or Beckman space. We do not have for HB. That's the main problem with HB. We do not have access to many elements of them. Some of them we know. For example, the kernel functions we know. We know under some conditions polynomials are there. And under some conditions, not all polynomials are there. Some of them are there, not all. So these things we know, but characterizing all the elements and have a clear criteria like the one we have for the Hardy space, no, still we don't have. And that makes it difficult to prove theorems for HB. And there are some other examples too. So it is important to have results like this. A function is given, we verify the properties, some properties that we are looking for, and then this is a guarantee that the function stays in the space. This is what we want to do. And to do this, we need the general notion of convergence of a net. We briefly discussed this before. Just as a reminder, a general net X, the index set I is a directed set. For us, it's usually subsets of a bigger set, not all of them, some of them. And the relation here is the inclusion. But the property, the important property that we need I to possess is that if I1 and I2 is in I, then there is an element I such that it's bigger than both. This is the crucial property that most of the time we use when we are dealing with a sequence on the integers 1 to 3. This is trivial, any two integers, I mean, take the bigger one. And when we are dealing with subsets, usually it's closed under the union. I1 is a subset, I2 is a subset. For I takes the union of I1 and I2. So in that case, it's also what we want to have. It's trivial, but in abstract setting, the Moore-Smith convergence that we mentioned last week, the crucial property that we need to have is this one. Any two elements have something which is bigger than both of them. And what does convergence mean? What do we mean by lim x iota and limit on iota is equal to x? This means that, I mean, the epsilon delta definition that we have before, it's written like this here. For every epsilon, there exists a iota 0. Which depends, of course, on epsilon, and it may depend on many more parameters, but at least to the epsilon here, such that if our index is bigger than or equal to iota 0, then the distance is smaller. We are dealing with complex number here, or at most with norms. I mean, either this or this is less than or equal to epsilon. The distance between x iota and x is big. For all parameters or for all values of iota, which is bigger than fixed one. It needs a bit of practice. It's not the same as sequences. There are major differences between them. And if you're not familiar with this, many mistakes easily can be made. And for example, one of these, which is, I mean, a common one, is that for sequences, when we have lim xn equal to x. And any epsilon given, there is an n0 as above, such that n bigger than this index, then the distance between xn and x either absolute value or norm is less than epsilon. What is not counted here, I mean, the indices for which this is not true is a finite number of indices, is at most from 1 up to n0 minus 1, at least here, the indices which are not taken care of. The rest, for the rest, it's true. However, this is not the case here. This is not the case here. If iota is bigger than or equal to iota 0, then okay, that works. But what are the indices for which this is not true? Which indices are not counted here? Not necessarily finite number of them. It could be infinitely many. And that's important to keep in mind. Okay. So for this, we have to start, we have a proposition to make us ready for this type of convergence. Proposition. Same setting as before, H is an RKHS on X. G is in H. And for each finite set in X, we let G index F to be the projection of G on HF. Again, recall HF is the span kx1 up to kx. The finite set x1 up to xn. Or it's, because I didn't mention x1 up to xn, it's better to say kx, x is in F. F is a finite set. This is better. So for each finite set, we project G onto H of F. So we have, now we have the net G of F. Again, the net G index F. When F is on the set of all finite subset of G. And here is the result. Then this net converges to G. See, it's not a sequence. You can imagine even in the form of trees, but be careful even if we imagine finite set. Trees means stuffs like this, I mean, or here. This is a finite set. This is another finite set. This one is the union of both. And it can, I mean, have many branches. Like it can be very, very complicated. And a good thing about imagining like this, imagining like trees, is to see that when you consider if this is your F0, all the F which are bigger than F0s means this one, I mean, all the one which are above, those which are not counted can be infinitely many. None of these are bigger than or equal to F0. And it can be many, many, many of them, contrary to what we have in a sequence. Well, still we have the limit of GF as a net equal to G. And the proof is a good exercise of doing limits with nets. And here is the way we do it. We saw before that the kernel functions are dense. Before that, if we consider kx, not for finite, x in x, all of them, and span. Well, a span, it depends which book you study. Sometimes a span means just linear combination. Sometimes it means linear combination and with closure. Well, to make it more transparent, I put the closure here. We saw this before, that the linear combination of kernel functions is dense in this space. So it about maybe 3 weeks ago. And therefore given epsilon bigger than 0, there is x1 up to xn, and also there is in x scalars alpha 1 up to alpha n in C, such that norm of G minus sum I from 1 up to n alpha I k xy in H is less than epsilon. That's the meaning of being dense. True. And look, I don't say that this combination sum I from 1 up to n alpha I k xy is the projection of G onto F. F is the finite set x1 up to xn, and H of F is the, let's call it F0, a span of kx1 up to kxn. Here, closure is not needed, it's finite dimensional. More space. Okay. I don't say that the combination I obtain is the projection, but I know that the projection is the best one. I mean, if I consider G index F0, which means the projection of G onto this space, then I know that the norm of G minus G of F0 is less than or equal to the norm of G minus anything in that space. Sum I from 1 up to n beta I k xi for any beta I. That's the meaning of, hidden in the meaning of projection. In particular, norm of G minus GF0 is less than or equal to put alpha I, which is less than epsilon. So the choice here is a good choice. If I replace it by the optimal one, still it's a good one. G minus even better, but it really doesn't matter. The good thing is that it's less than epsilon. For F0. Now what happens if we consider a bigger set. Here, less than or equal means that subset. If we consider a finite set, which has more element than F0, well, clearly, HF0 is a subspace of HF because we have more elements in F. And what we can say about GF? I mean, G index F is the projection on HF of G. And since it's a projection, it means that, assume that F is equal to, say, x1 up to xn, and these are the elements of F0, a little bit more, say y1 up to ym. It's bigger. The projection means that the distance between G and GF in H is less than the distance between G and any other element in that space. Any other element means that the sum J from 1 up to n, beta J, kxj, and k from 1 up to n, eta k, k, yk. This is an arbitrary element of H index F. For any combination, no restriction on beta and no restriction on eta. This is always small. In particular, we can take all eta k to be 0 and choose beta k such that this combination gives us GF0. In particular, take eta k all equal to 0 and beta j such that the sum j from 1 up to n beta j kxj is equal to j index f0. This is possible by the definition of g f0. Therefore, G minus G index F is smaller than G minus G index F0. And we know this is small. Therefore, for any F bigger than or equal to F0, G minus GF is less than epsilon. That's precisely the meaning of lim GF equal to G. Well, before our next break, let me recall you the relation or partial ordering that we have in the set of self-adjoint matrices. So we consider matrices A such that A star equal to A and B star equal to B, I mean, these matrices. In this setting, we saw the meaning of A bigger than or equal to 0. We can say that this is equivalent to say that all the eigenvalues are 0, or if you wish, inner product of AX and X equal to 0. And then definition, I mean, A is less than or equal to B. Here it means that the matrix B minus A is positive. If B minus A is positive, we say that A is less than or equal to B, and it has all the properties of a partial ordering in the family of self-adjoint matrices. Means that it's transitive and A is less than or equal to A, and also you can multiply by a positive scalar. This is something that I will need here. Okay, let's have another break and then we come back to this after the break.